now going to talk about WindTail. WindTail is an interesting piece of Mac malware. I described it briefly in the blog, and we talked about how it was targeting individuals of a Middle Eastern government. The last live stream, we looked at how it persisted and how it basically exploited Mac systems. So now what we're going to do is we're actually going to dive into reverse engineering to look at its install mechanism and then also reveal its capabilities. So yes, we're not done yet. Come on, it's only been an hour. I will post this online if you need to bail. So let me just hop over to this VM. And hopefully this is an illustrative example of how I basically go about analyzing a piece of Mac malware. So feel free to ask any questions. This is kind of a technical deep dive, but I'm going to hopefully explain exactly what I'm doing. So we're going to start with the malware, and the malware is a binary called final presentation. This looks like a PowerPoint presentation, right? Is it a PowerPoint presentation? No, it's an application. It's an application whose certificate has been revoked because Apple has now decided not to run it. Cool. So this sample is available online for download via the Mac database, the Mac malware database. So what I've done is I've opened this in a disassembler. And what a disassembler does is it takes the binary code of a binary and converts it kind of back to assembly code, or if you have a decompiler, back to C code. So this can then provide, if you understand how to read C code or assembly, you can see basically what the malware is doing. So this is called static analysis, right? So what we're going to do is we're going to start at the beginning, and I apologize, this is a little small. I'll copy and paste this into a text edit window so that we can read this. I haven't figured out how to make the disassembler bigger. The disassembler I use is Hopper. So again, we've copied the malware into this and said disassemble. Make this hopefully larger so you can read this. So this is the decompiled code of the malware. We talked about this first part last time. This is basically just generating a unique ID for the malware and then saving that to a file. At the very end of this function, the application did finish launching, which is automatically invoked by the operating system when the application is launched. It invokes a method called tuffle and then spawns a thread to execute mydel. So we'll look at these. So what I've done in a VM is I've gone and I set a breakpoint on the tuffle method. Actually, that's not exactly true. Tuffle method, here we'll just look at this again, calls app delegate alloc and then app delegate init. So it's initializing an app delegate object. So we can now look at what this does. Again, we can do this in the decompiler. Again, I'll copy and paste this into the text edit window so we can see that. So the application delegate init function calls something called CP, a method called CP. So again, in the decompiler, we can double click on that. That will open the CP method. Again, I'll copy that here so we can see what this does. Again, if you don't read C code, if you understand API method names, you can kind of even just go Google some of this stuff and figure out what it does. So CP likely stands for copy, right? And so what this method does is likely copy or install the malware. And that's exactly what we'll see the malware doing. Quick question. Okay. How trustworthy is Xprotect regarding APTs? Okay. Xprotect is Apple's built-in malware detection utility. Yes, Mac actually has built-in anti-malware detection. The problem with Xprotect is a fewfold. First and foremost, it only will scan applications that are downloaded from the internet. So if there's a 0-day vulnerability that abuses a flaw in Safari that the exploit downloads the payload, XProtect won't even scan those. So it only actually scan loads files that the user will manually download. So there's the first shortcoming. The second shortcoming is it's very basic, it's signature based. So anytime there's a new piece of malware, XProtect is not going to know about it or detect it. So for APTs that are going to have advanced exploits, and if they don't have advanced exploits, they will at least have custom malware. XProtect is not going to detect that. So good question. XProtect is good for the average Mac users and will prevent well-known adware, well-known malware from infecting users. But for advanced attackers, XProtect really is not an obstacle at all. So as Josh says, you can't rely on XProtect. Perfectly well said. Okay, so back to this CP routine. Just close this. We can see that what it's doing is it's getting a path, and we'll see this all in the debugger. So we'll see this happening live. It's getting the path to the malware via the bundle path. It's then invoking the UP method to decode or decrypt some string. It will then check if some file exists, and if the file does not exist, it will copy some item somewhere. So again, this is likely how the malware installs itself. So we can hop over to a VM and we can actually see this happening in action in a debugger. So the debugger I use is something called LLDB. And what a debugger is it's something that basically can allow you to execute any binary one instruction at a time. So you can analyze the malware as it executes, but one instruction at a time. So you can very easily see exactly what you're doing. So this is dynamic analysis. So what we're going to do is we're just going to step through these instructions. The NI command is next instruction. And don't worry, you don't have to understand assembly code here. We'll basically see that because this is Objective-C, there are some very nice method names and strings. So for example, here we can see that this instruction is going to move the NS file manager string and then the alloc into certain registers. So we can basically now assume that it's going to execute the NS file manager alloc. So it's going to allocate a new NS file manager object. And if we go back to the disassembler, and what I'm going to do is I'm just going to switch to assembly mode. I'm going to hit G and go to that address. We can see that this is so small. Okay, I'm going to switch back to the text edit mode. We can see that, yes, look, the CP function is allocating a NS file manager object. So again, what we're doing is we're executing each instruction. Now, it's important to note that decompiler will generate C code, C-type code. Disassembler will generate assembly instructions. So for each line of C code, there's going to be multiple assembly instructions. So as we do that NI command in the debugger, we're actually executing one assembly instruction at a time, not one line of C code. So you can see we're going to allocate now the NS file manager object. We're going to init it. And now you can see, okay, here's the logic. They're going to call the NS bundle main bundle API. And what we can do is when we step over this call instruction, the RAX register will hold the result of that method. So what we can do is we can type NI to step over that and call instruction, which means that will be executed. And then we can type PO, which says print object, and we can pass the register we want to print, which is RAX, and this will print whatever that function returned. And in this case, it was calling bundle path, which is the path to the application. So basically, it will, as you can see, be the full path to the bundle. So you might be wondering, okay, Patrick, how did you know the RAX register contains the return value from any function call? This is part of what is called the ABI, the Application Binary Interface. And basically, when you build an application for Mac OS, the compiler builds a binary with this logic. So any binary you run on Mac OS, as long as I know, if it's compiled, whenever a function returns, the return value will be in the RAX register. So knowing this, any piece of malware you're analyzing, if you step over some function and you're not sure what that function did, if that function returns some value, some object, you can simply step over that call and then dump the RAX register to see. So here's another example. We're basically going to skip over this. We're going to get to the UP instruction, sorry, the UP method. And the UP method is going to decode or decrypt some string. And we can see that right here. We're right at this instruction right here. So this hopefully illustrates the power of dynamic analysis. If we look at the decompilation via static analysis, we just see this encoded encrypted string. We have no idea what it is. But via dynamic analysis, we can simply execute over the UP command, and then the return value is going to be the decrypted string. So really, we don't have to worry about how the encryption is implemented. We don't have to write a custom decryptor. We just step over the UP command, and then we type PO RAX to print out the return object. And what do you know? It's the decrypted string library. This is likely where the malware is installing itself. Makes sense that the malware would want to hide this information. But again, by dynamic analysis, we can simply view what the user is doing. Awesome. Okay, so let's keep stepping through. We now know they decoded that string. They're now going to call the string with format API. So one last thing, when you call a Objective-C method, just like the RAX register will hold the return value, other registers hold well-defined values before the call. So the first one is the RDI register. So if we do PO RDI, this will print the value of the object in RDI. And this will be the object that we're executing the method on. The RSI value will have the name of the method that we're going to execute. So now we know we're calling the NS string, which is an Apple string object. We're calling this string with format method. Now the string with format takes various parameters, which are going to be an RDX, RCX, R8, and R9, depending, of course, if the method contains several parameters. So what we can do again is we can type PO RDX, and this will print out for us the first parameter. Okay, so we can see it's a format string with 1, 2, 3, 4 parameters. So if we print out the next parameter, what's this going to be? It is the first value that's getting passed as that format value. And again, we can continue this. We can do R8, R9. Cool. So now we can see basically exactly what is being passed to this NS string, string with format method. Now we can also just step over it, and this returns the formatted string. So if we do that and then type PO RAX, this will print out the formatted string. So we can see that these percent, I don't even know what that symbol is called. @ yeah. The @ is replaced with users, library, / and then the name. So what the malware is doing here is building up a full path to where it wants to persistently install itself. Awesome. So now we can step through these various APIs. Again, I'm just skipping over a lot of this code. They're basically going to check if a file exists. If the file does not exist, what they're going to do is they're going to invoke the copy item at path method to copy themselves, perhaps from the download directory or the desktop, to the persistence location, which is /users/library. So again, we're going to stop right before they make that call. Again, PO RDX is going to print the object. This should be a file manager. Yeah, what is this? A string class? Is this a string? Yeah, so it's a string. The method they're going to execute is in RSI. And then, oh, had this backwards. Sorry. I always get these mixed up, so it's good to write these down. RDI has the object. RDX is the first parameter. So if we do PO RDI, we can see we're going to invoke a method on the NS file manager. We're going to invoke the copy item at path. And again, if we print out the parameters, the first one being an RDX, we can see, okay, this is the item at path. So this is the source path that we're going to copy, right? This is where the malware currently is. And if we print out the second argument, which is an RCX, This is the destination. Cool. So now we can see exactly where the malware is copying itself to. And again, remember this library component was encrypted, so via static analysis, we couldn't easily determine what it was doing. But via dynamic analysis, we basically just come to where it calls copy item at path, and we dump the parameters, and we can see exactly where the malware is installing itself. Kind of cool. Now, you can actually come over here, and we can run fs usage. The fs usage is a built-in file monitor command. So we can execute it with the -w, which says wide -f. We say we want to modify the file system. And then we pipe that into grep because we only want files associated with our malware, which again is called final presentation. Well, let's just look for final. So I'm going to put in the password for this VM. Okay, cool. So in theory, when we step over this copy instruction and come back to the file monitor, we can see that, yeah, exactly. The malware basically opened itself, made a directory, and then wrote the file to there. So again, using a file monitor, you can also observe what a malware is doing. So again, the fs usage is the utility that you can use to monitor file actions. Again, it'll monitor all file actions on the system, so it's always good to filter, for example, piping it into grep. For example, giving it the name of the process. In this case, our malware, again, is called final presentation. So we grep on final, which will filter on just processes or files that match on that. So if we come back to here, now we can do an ls, which will list the directory contents of library, and we can see, was it? Did it not? What was it? User library final presentation. Okay. Yeah, there it is. So again, we can see, okay, cool. And if we go there in Finder, we can probably see it as well, because I don't think the malware hides it. So we can type Shift Command G, enter a path, go to library. Again, not a super stealthy place with the malware. But again, what we're doing is via the debugger, we are watching how the malware is installing itself. The last live stream, we talked about persistence. And at this point, the malware has already persisted. So if we open the user groups and look at the login items for this particular user, we can see that the malware has actually persisted. It's funny, there's a bug in the malware, it persists itself twice, but I guess this ensures that it will really be running each time. Okay, so that's the CP method, and this again is how the malware installs itself. Via the debugger, we saw how it basically decrypted the string, built the path to the destination, and then invoked the copy item at path API to copy itself to its persistence location. Awesome. So the next thing we're going to do is we're going to breakpoint on another method, and we're going to observe what the malware is doing. Because at this point, we know that the malware is persisting, but we don't actually know what WindTail does. Like, what is its goal? Is it going to install a cryptocurrency miner? Is it going to steal my passwords? Is it going to format my system? If you're doing malware analysis, it's always good to know kind of what the malware does. So we're going to start on a method called yan. I think the attackers just made up random names for this. And again, I'll make this bigger. Hope you can see that. We can basically see that the yan method calls the yoop method on multiple strings. Again, via static analysis, no idea what this does. We can go look at the yoop command, and there's two of them. Let's just look at the first one. We can see it decrypts. It looks like it does some AES decryption with a key, right? It's like, I don't want to deal with manually decrypting AES. Let me just via, again, dynamic analysis, execute this code and see what's there. So what we're going to do is we're going to get the address of that method. So that's at 1000238B. I'm going to go back to the debugger, and I'm going to put a breakpoint on that. So you can do that with the B command. A breakpoint basically tells the, let me move this a little more so you can see it. Breakpoint basically tells the debugger to stop when it gets to this instruction. Since a debugger will execute each instruction, and there's like, tens of thousands of instructions in a piece of malware, what you normally do is you find exactly where you want the debugger to stop and put a breakpoint there. And then you just tell the malware to run, and then the debugger will stop when it hits the address you specify, and then you can manually step over, because otherwise it would just be way too arduous. So we type B, and then we put the address of the method, and you can see that it says, okay, I put a breakpoint here. If we hit C for continue, we should hopefully hit that breakpoint, and we hit it right away. Remember, the RSI register at an Objective-C call will have the name of the method. So very easily, we can confirm, yes, we are at the YAN method. Again, recall the YAN method basically decrypts all these strings. So what we can do is we can step over all of these manually, or we can actually simply say finish. And finish will tell the debugger to execute everything in that method block and then stop when it's done. So now it's executed this, and remember, when a method executes, what's in RAX, whatever that method returns. So if we go back to the disassembly, we can see that it decrypts all these strings and then adds those into an array and then returns that array. So we can just print out that array to see everything that the malware has decrypted. So if we do that, woohoo. And what do these look like? File extensions. What kind of file extensions? Files that perhaps malware may be interested in accessing. All right, question. Funny how they use the PowerPoint app icon rather than a document icon, even though the file's name is made sound more like a document. True. Why wouldn't you always use dynamic analysis, simpler malware? That's a great question. So dynamic analysis, and I kind of answered this as you mentioned. It's great, but it can take a lot of time. So what I normally do is I will often do some brief static analysis to look for interesting points in the malware. For example, this YAN method we saw kind of did a bunch of decryption, right? It's like if you see a method like this, if you do a lot of malware analysis and look at legitimate code, you're like, okay, these are obviously base64 encrypted strings. Like this is a very interesting chunk of code, but via static analysis, you're not going to be able to figure that out. So then I'll hop in a debugger and step through that. So what I normally do is I use static analysis to locate points of interest, and then I will use dynamic analysis to go set breakpoints on those to execute through them. So again, via static analysis, you might detect the VM detection code. You then can go in and you can patch that out, or you can step over that via dynamic analysis. So normally I do both in conjunction. Okay, so that's the YAN method. Again, we stepped over that and we can see, okay, it's decrypting all these interesting file extensions. And these are document file extensions that probably have interesting stuff from a malware's point of view. So I'm going to set a breakpoint on another method now called the df method. And I've done some initial analysis on that. This is how I know all the names of these functions. So if we go to the df method, we can basically see it is doing two things. It's pretty basic function. So it first calls an isOK method, and if that isOK comes back and says okay, it executes a method called fist. Again, these are probably just arbitrary names. If that fails, it sets a timer to execute another method. So basically says I'm going to check if something's okay. For example, that the command and control server is up. And if the command and control server is not up, I'm basically going to sleep, set some timer, and then maybe try again in an hour. That's fairly standard stuff. So the reason we're going to execute this in a debugger is because this isOK is going to fail because I believe the command and control server is offline. But I'll show you, we can actually modify the code, rather the registers, so that this code in here executes, because we want to execute the fist instruction, even though isOK is not okay. So the first thing we do is we get the address of the df method. So we can do that from, again, the static analysis. We then come back to the virtual machine. We type B, and we put the OX in front to tell it it's a hex address. Put the address, hit enter. This will set a breakpoint. Again, this tells the debugger, whenever this instruction at this specific address, this line of code gets executed, please stop so that I can examine this. If we then hit continue, we can see that very quickly we execute that again. Again, the RSI register will have the name of the method. So we can execute that just to confirm, yes, we are now inside the df method. And what we can do is we can start single stepping to get to that is okay method. Again, we can see right here, just a little more, the string is okay, and then we're going to invoke that method. So we can step over that right here. We're going to step over that. And then what register has the return value? RAX. So we can say reg read RAX. This will print out the value of reg read. We can see that it's 0. This means that this code check is going to fail, right? Because it's equal to 0, not equal to 0. So it's going to skip. It's basically going to go to sleep and not do anything. We want it to do something. So we want to force it to execute this. So what we can do in the static analysis, we can actually change the register value of RAX because we're in a debugger. We can do whatever we want. So if we do that via the reg write RAX 1. Now, if we print out the value of RAX, we can now see it's 1. So now the code is going to basically test the RAX register to see if it was 0 or 1. It was 0, but we changed it. So now it's going to execute that fist method, which is what we wanted it to do. So now what we can do is we can set a breakpoint on the fist method. Kind of a funny name. So where is fist? Okay, it's down here. And let's disassemble that. We'll come back to that in a second. Again, we type B for breakpoint, OX to tell it's a hex address, and then we copy and paste the address of that method from the disassembler. So now we have a breakpoint on the fist method. So we hit continue, and it says, okay, it breaks on breakpoint number 6. That was the breakpoint we just created. So now we can start executing through the fist instruction. So again, if we hadn't modified that RAX register, we would have never hit this method because that is okay method did not return okay. So again, another really powerful capability of dynamic debugging is you can still force malware down certain paths that it would not normally execute. For example, if the command and control server is offline, or if it has anti-VM logic, you can basically step over the method that checks if it's in a VM, and then change the return value to be like, no, I'm not in a VM, when in reality you really are. I'm not going to answer that. So what does the fist method do? The fist method is, go back to the disassembler. It's rather long, and I'm going to copy and paste it into a text editor window so that we can increase the font size. Oh, cancel. Okay, you said okay. So again, what I normally do is a lot of this assembly code you don't really have to worry about, is just look for method names, because Apple's methods names are very verbose and descriptive. So what do you think contents of directory at path does? It returns the contents of a directory. Okay, what do you think string by appending path component does? Okay, it makes a string by adding a path component. You can see it's checking a path extension. It's removing some object. It's executing some sys method, adding some object. So we can very quickly, by looking at this, first and foremost, by seeing it invokes the content of directories at path, we can say, hey, this is likely going to enumerate files on the file system. Cool. So what we can do is we can set a breakpoint on any of these methods. For example, this path extension method. So we come back to here, and bear with me for a second. I'm just going to look for that call to the path extension. It's okay, right here. So now I'm setting a breakpoint within the method. It's a really big method. We could have stepped through it all, but again, it's easier just to do that. B, OX, blah, blah, blah. Okay, cool. And then we're going to hit continue. Okay, so now it broke at the call to the path extension. I'm going to print out RSI just to make sure. Okay, PO RDX is the first parameter. We can see that it is a file object. And if we do PO on RDI, we can see here's the name of the file object. So we can see it's basically looking at the DS store, which is the first file in any directory. We're going to step over that. And then what we can do is, what is this right here? Yeah, we can see that it's basically going to compare to see if that extension matches doc. Remember, doc was one of the file extensions that the malware was interested in. So again, we can step a little more to get to this compare routine. We can see it is comparing. Where am I at? Compare. Yeah, that should work. Oh, x/s RSI. It's calling compare against, I'm going to guess, doc. Amazing. And actually, if we print out the object that it's comparing against, it's in RDI, it's nil or blank. And that is because ./ds_store, which was the file name we currently have, which was somewhere up here, doesn't have a file extension. Makes sense. So basically what it's doing is for every file it finds, it's checking if that matches one of the file extensions that was of interest. So we can come down a little further and we can set a breakpoint, for example, here. And this should be executed. Let's do br delete to delete all the other breakpoints. Yes, B, set a new one. Awesome. And then if we step over this, we can see that it found a file that matched one of the file extensions of interest. For example, it found an RTF document. Cool. So at this point, it should be fairly obvious that the malware has this set of file extensions it's interested in, for example, docs, PPTs, RTF. And what it's doing is it's enumerating all files on the file system. And for ones that match those extensions, it's going to do something with those. So let's see what it's going to do. So the first thing let's do is let's start up a process monitor. I use proc info. Got to run this as root. It's a process monitor I wrote. It's going to basically just monitor anytime there's a new process. We're going to come back to here. We're going to delete all the breakpoints. And we're going to set one more breakpoint on a method called zip. What do you think the zip method does? Yeah, exactly. Zips things. So we can set a breakpoint on that, box, the address of zip. If we come back to the disassembler and we look at the code, again, I'll copy and paste this into a bigger window, we can see that the zip method basically looks like it invokes the zip utility with a bunch of command line parameters. So what we can do is we can set a breakpoint here, and then we can step through this code to see exactly how it's executing the zip method and what it's going to do. So again, we set a breakpoint on here. We hit C for continue. Cool. Broke at the zip method. So now we can just start happily stepping through this. Again, I usually just step over and look for, okay, last path component, string by appending, blah, 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 blah. Till I get to maybe something interesting. Did I step too far? Well, the good news is, oh no, I think it's right here. Okay, it's going to create an array. So we're going to step over that and we can print out the array. Perfect. So this is the array of arguments it's going to pass to the another method, which is going to execute this. So we can see it's going to execute the built-in zip utility. The first argument is the name of the archive it should create, which is the file name it found, .zip, and then the full path to the document. Again, this is a document on the file system that matched one of the file extensions of interest. Good question. Where is it sending it to? Maybe it is sending it to. Awesome. So if we hop over to, if we step a little more, we can see it's going to invoke a method called start process. Wonder what that does. And we can just hit continue. It'll run for a little bit. We come over to the process monitor and we're going to look for zip. And we can see that our process monitor has also captured, sorry, I'll move this over, has also captured this action. So again, this just kind of confirms what we saw in the debugger, that yes, the malware basically executed the zip command to zip up a file. And we can see that it hit it again because it's probably going through and zipping up all the files. So the final question is, okay, what is it doing with this file? Because now we can say, hey, we know that it's zipping up these utilities. So it turns out there's another method called upload. The malware authors really made it rather easy for us in this scenario to analyze it because the names of their methods are very verbose. So if we look at what this does, again, you don't have to really often worry about a lot of instructions. You basically can just look for strings and get an easy idea of what's going on. So for example, you can see it's appending something called computer name username. I wonder what that is. And then it's referencing curl. Curl is obviously a built-in utility that can allow you to, for example, upload files. So it's likely, we can assume via static analysis, that they are going to exfiltrate the zipped files via the curl command. So we're going to set a breakpoint on upload so that we can step through this to see exactly, for example, where it's sending this, right? There's nothing in here that immediately says to me the address of the command and control server. But if we put a breakpoint on this start process routine, we can probably see exactly where curl is sending it to without having to do a lot of reverse engineering. So again, the power of dynamic analysis, but showing how static analysis basically enables this. So I'm going to get the address of this upload method and then hop over to the VM. Hope you're seeing a pattern here. Put a breakpoint. I'm going to delete the other breakpoints. BR delete deletes the breakpoints. B and then the address of where you want it to break. Hit C for continue. Twiddle our thumbs. Hopefully this eventually hits. Maybe, come on. So, okay, maybe it gave up. Well, we'll see if the process monitor caught it. Ah, there it is. Oh, no, we got a breakpoint. So it's probably uploading each file individually and then perhaps, waiting 60 seconds between each upload so it doesn't like crush your network. So again, we've now broken at the upload method. So again, using the NI, which is next instruction, we basically are telling the debugger to execute over each instruction. Again, what I do is, as I do this, I just look for usually strings on the right-hand side of the screen. For example, you can see we're calling release alloc. I want to get to the call where it invokes the method. However, here we can see it's calling string append, so it's appending some string. So let's step over that method, and then again, RAX contains the value that method returns. So the value that was returned by string by appending string. So we can see that they've built this string vast equals @temp step template pdf.zip. So this is likely the file that we're going to exfiltrate, right? In the vast parameter. Keep stepping, they call this again. PO_RAX to print out that string. OD, some number. This is actually the UUID of the implant. And I know that because I did some other analysis of that. If we do less cat, final presentation contents, resources, date.txt, we can see that there is that. Does this match? Yes. Phew. But yes, this is the UUID, the unique identifier for the implant. So just hold that thought. And then finally, we're going to execute the string append method one more time. Step over that, print out the RAX. And we can see this is the name of the computer and then the name of the user. Question, does it overwrite any logs to cover its tracks? I have not seen it do that. It's a relatively sophisticated piece of malware, but not super incredible. Like, this is not something that the NSA would write. They would be embarrassed, theoretically. But, it gets the job done. So a lot of Mac malware we see is not incredibly sophisticated, but I will caveat, perhaps our detection capabilities are not that sophisticated, meaning the really stealthy implants we might just not be detecting. But to answer the question, I have not seen this specific malware overwrite any logs. I've seen some Mac malware do some basic things where they'll like delete terminal history and some basic, let's say, anti-forensics type stuff, but nothing very sophisticated, at least on the Mac side of the house. Okay, so where are we? We are executing through that. You're going to see we're going to call over this. If we, again, RSI will hold the name of the method. So we're creating an array with objects. So if we step over this, this will give us the array that was just created. So again, RAX, we can print that out. And this is the array. Awesome. What do we have? We have curl -f, vast, blah, -f, od, blah, -f, kl, blah, string me.com, blah, 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 .php. Perfect. So now we can basically see exactly what the malware is doing. It's exfiltrating at least information about this file by using the curl utility. So we can see that if we come back to our process monitor. Let me just hit Control K to clear that. And if we hit continue to execute that and come over here and look for curl, we can see that the process monitor has detected what we saw in the debugger, which is the malware exfiltrating information about the files that it created. Awesome. So now we basically can comprehensively describe what exactly the malware is doing. It's basically looking for any files on the file system that match any of those file extensions of interest. So we decrypted those file extensions. We saw, for example, it was doc, ppt, .db, .text. And then via the FIST method, it enumerated all the files on the file system, and for each file checked if that file path matched that domain. For ones that did, for example, step-template.pdf, it invoked the zip utility to create a zip of that and then posted information about that to this string to me URL. Now, it's not clear. I think it's not actually uploading the entire file at this point. That's probably for, obvious reasons. They don't want to exfiltrate every PDF because on Mac OS, there's a lot of PDF documents that are legit. For example, the step template, I believe, came from, the Automator framework. I think we saw that in the debugger. So what's likely happening is once the attacker gets a list of all these, they can basically, cast a very wide net. They can basically go through, peruse, and say, okay, these are all the PDF documents on the file system. Ignore all the ones that are Mac OS ones. But okay, hey, there's this one called topsecret.pdf or, top secret contacts or file records or, dossier.pdf, things of interest. And then likely they can task the implant to exfiltrate those specific files. Again, this is normally how more advanced cyber espionage utilities work. They will enumerate a lot of things and then send that back to attacker. And then the attacker will manually analyze those or pass those on to analysts. And then the analysts will say, okay, these are the files I want to collect. And this is obviously just to reduce overhead. You don't want to collect every single PDF on a system because that's going to generate a lot of network traffic that's likely going to be detected. So that is WindTail. I'm going to be blogging about basically what we just talked about in these coming days. So feel free to kind of come back and read that blog, and hopefully, if you missed, some of the things, that will provide more information. But again, I thought it was just an interesting case study where we could illustrate how we use static analysis, disassembler and debugger, to complement dynamic analysis, and how we could set breakpoints on methods of interest. And then because it was written in Objective-C, method names are very verbose, and a lot of objects, for example, dictionaries and arrays, contain a ton of information. So we could just step over the decryption routines. We could use the process monitor to see. So again, we very quickly analyze this decently sophisticated piece of malware. All right, so that is a wrap in terms of what I wanted to talk about. We do have some time, though, just to chat about anything you all would like to chat about. So let's do some Q&A. Again, thank you to the friends of Objective-C. Okay, so just looking at some questions. Make sure we can read this. First, thank you so much for all your feedback. And thank you also for joining me. Like this would be really awkward if I was just talking and no one was watching. So thank you for spending time to yeah, connect and join. Great questions. I love the interactive. Obviously I'm very passionate about this stuff, but I wouldn't do it if you all weren't interested. So mahalo. Again, we'll be doing this every Tuesday around this time. I generally try to pick topics that are things I'm working on, things I'm blogging about, new exploits, new vulnerabilities, that as well. I also then post these to my YouTube channel. So let me just post the link to that. I'm trying to think. Wait, it's at the end of this guy. We just grab this link. Oh my God, this blog post is so long. Let me just do that. Okay, here's the YouTube channel. More pupware. I hate pupware. Pupware is potentially unwanted software, basically adware. Problem is there's so much adware and it's all just like shit. Like, I mean, it's like, not shit in terms of it's poorly written, but it's just like a rabbit hole of like obfuscation and crap. And you get to the bottom and like its entire goal is to like hijack your Google search results. And I'm kind of like, okay, that was a waste of my life. So generally, I like to focus more on malware. For example, WindTail, which we just looked at, it's doing cooler things, in my opinion, cooler things like enumerating files on the file system, exfiltrating stuff, keyloggers, that kind of stuff. So yeah, if you run across any interesting files, you can always send them to me and we can talk about them. If you have topics of things that you would like to wait, no, don't want to do that. Twitter. Twitter.com/Patrick Wordle. You can hit me up on Twitter. And also definitely subscribe to this Twitch channel so you get notifications when I am. Oh, pupware. Hannah, you're wanted on the internet. Okay, we love pupware. I don't know if she likes. You want to hack? You want to hack? So Havana's actually the real brains behind the operation. When I'm not streaming, she's like, I think she's like the Kung Fu master in like Kung Fu Panda, right? She's like, no, she's not beating me with a stick, but she's teaching me everything I know. So, right, puppy? She's like, I want to go chase chickens. Okay. Bye. Bye. Go get a toy. Go get a toy. Oh my God. Okay. Awesome. Sweet. Again, thank you so much for your feedback. I really, really appreciate that. Yeah, and I think this is a great way to share the information I'm talking about. I usually like to blog as well, so that there's kind of a more perhaps articulate method to perhaps my madness. But I really think the hands-on streaming is cool. One, because it's super interactive with you all, and then also I hope it's kind of a hands-on example of basically what I do, how I do my malware analysis, and how I do those kind of things. So again, thank you so much for joining. Really appreciate it. Also, thanks as always to my amazing friends of Objective-C, also Digita Security, and Havana. And I will see you all next Tuesday, same place, same time. So thanks again. See you next week.